4-6, formalizing relations and functions. So our objective for this section is to determine whether a relation is a function and to find the domain and range and use function notation. Our essential understanding is that a function is a special type of relation in which each value of the domain is paired with exactly one value of the range. Okay, so before we start, we need a little bit of vocabulary. So first, a relation is a pairing of numbers in one set. So it could be anything, could be numbers, could be letters, fractions, decimals, doesn't matter. Okay, we're going to put all the things in one set and we're going to pair them together. The first thing is called the domain with numbers in another set called the range. So in my first set, I have elements of the domain and I have elements of the range, and things in here get paired with things in here to give me an input value and an output value, or an x and a y value. So a relation is often represented like this as a set of ordered pairs with x comma y. In this case, the domain is the x values and the range is the y values. And that's kind of how most problems will work. When you look at a set of numbers, my domain is going to be the x values and the range is going to be the y values. So identify the domain and range in each relation and represent the relation with a mapping diagram, and then we're going to decide is a function. So my domain for this particular set is going to be -2, 0, 4, and 5. My range for this set is going to be 0.5, 2.5, 6.5, and I don't need to write 2.5 again. Okay, domain is my x values and range is all my y values. So now to make a mapping diagram, right, this is just listing my domain and range. Okay, to make a mapping diagram, we are going to take the domain, okay, make a little group of my domain, and usually we like to put it in order from least to greatest, so 0, 4, 5, and we should do that inside the sets too. And my range, all right, we're going to make another little box, and my range goes from 0.5, 2.5, and 6.5. And I'm going to simply map which one goes with which one. So from my first point right here, -2 goes to 5, 0 goes to 2.5, 4 goes to 6.5, and 5 goes to 2.5 as well. So from this map, I see that each element in the domain goes to one element of the range, right? All the x's are different. If I look at my values here, yeah, the y's are the same. Both of these points have 2.5, but 0 is only mapped to one number. This is a function. Okay? That relation is a function. When we look at the next one, the domain is 6, 4, and 5. Notice that 6 happens twice. And my range is 3, 4, 5, and 8. Again, trying to put them in numerical order. So my domain and my range, if I make a mapping diagram, my domain is 4, 5, and 6. And my range is 3, 4, 5, 8. 4 goes to 3. 6 goes to 5. Should have went in order. 6 also goes to 4, and 5 goes to 8. Now you can see the 6 is going to two different values. So the domain value of 6 is getting mapped to two values in the range. And you can see that x repeats and it goes to a different number in the range. This is not a function. So when we compare domain and range, we always want to make sure that the domain only happens once, or each element of the domain only happens once, and is only mapped to one element of the range. So domain, we'll do this fairly quickly. Domain for part A is the x values, 4.2, 5, and 7. And this is not a function because you can see 4.2 happens twice, and it is being mapped to two different values. The range would be 0, 1.5, 2.2, 4.8. Okay, for part B, my domain is -2, -1, 4, and 7. And my range is -7, -4, 1, and 2. All of the elements in the domain are different, so this is a function. Another way to decide if a relation is a function is to look at the graph of the relation and use something called the vertical line test. So the vertical line is, I'm going to draw a vertical line straight up and down, and if it passes through more than one point on the graph, then for some of the domain value, there's more than one range value. So the relation is not a function. Okay? So in order to figure out if the vertical line test, if this function passes or fails the vertical line test, I'm going to have to graph each one of these. Okay? So I'm going to go -4, 2, put a dot. -3, 1, put a dot. 0, -2. -4, 1. Oh, sorry, -4, -1. And 1, 2. Okay? So if I were to take a vertical line straight up and down, okay, and move it, I could see that right there, the line hits more than one point. All the others are okay, but right there the line hits more than one point. So it does not, this particular relation does not pass the vertical line test, so it is not a function. Not a function. And I could have saw that easily by just looking that there are two x values that repeat with different y values. All right. So now for this one, I just have I have an equation. I don't have my output points. So if I want to successfully graph this, um, I know what it looks like, but if I wanted to successfully graph this, I'm going to have to find some output points. So let's make a table, okay? And let's plug in -2, -1, 0, 1, and 2 into my function. So let's actually go a little bit longer. Let's make this that y is equal to -x² plus 3. And then make my ordered pairs x comma y. All right, so y is going to be -2 squared plus 3. -2 squared is going to be +4. That becomes -4 plus 3 is going to be -1. So my input is -2, my output is -1. If I put that on the graph, little point. Okay. If I plug in -1, we get -1 squared plus 3. That gives me a +1. Make that negative plus 3, we get 2. So it's -1 comma +2. Okay? So -1 +2. If I plug in 0, that's pretty easy. We get -0 squared plus 3, which is 3. And I put a little dot. And then 1 and 2 are going to be similar to the first one. They'll be negative 1 squared plus 3. And of course, we're squaring the 1 first, so it gives me positive 1. Make the answer negative. Exponents come first, and we get 1, 2. And for this one, we're going to get negative 2 squared plus 3. It's going to give me the same answers as before. So when I graph this, I can see that this particular function is going to look something like a parabola. And this parabola, if I were to draw a line straight, if I were to draw a line straight up and down and take a look, there is nowhere on this graph that the vertical line hits more than 1 point, so it does pass the vertical line test. Okay? Is it a function? So for 2, 1, 2, 0, 1, negative 2, 2, and 3, 3. Well, just looking at them, looking at the vertical line test. So when we look at this, the vertical line never hits the graph more than once. Okay? So let's clear this off and look at the second one. So 0, 2, 1, negative 1, negative 1, 4, 0, negative 3, and 2, 1. And now my vertical line, I can clearly see that this line hits those 2 points. So this one is not a function. And shortcut, when we have data, to just look at the x values, and we could see that 0 repeats itself with 2 different values. This is not a function. Usually the vertical line test is a better technique if you have a graph only without the raw data like you have in A and B. Then it's better to use the vertical line test. Usually, if you just have the raw data, you can look at it and figure out if something is a function or not. So we've seen functions represented as equations involving x and y, such as y is equal to negative 3x plus 1. Below is the same equation written using function notation. And we have this symbols to represent y. Okay, this is called f of x. Okay, so we read this as f of x. The function f at this particular variable, the function evaluated at x. Letter f is the name of the function, not a variable. Okay, that's very important, and a lot of people make that mistake. Okay, the function, the f is just notation. And so is this x right there. That is just my input value, and I can clearly see that the function is in terms of x. Okay, function notation is used to emphasize that the function value f of x depends on the independent variable x. Other letters can be used. Most commonly, f is the most common, just like x is the most common variable that we use. But G and H are also good names for functions. Or something more specific, like in this problem, we have a function W of X because it represents the number of words. So W, good choice for the function, words. You can read in X minutes. So how many words can you read in 8 minutes? So let's look at this function. W of x is equal to 250x. Okay? So I know that my variable is going to be, my independent variable, the thing I want to evaluate is 8. So the way I do this is I want to evaluate w of 8. Okay? That means every place that I see an x, I'm going to plug in 8. So this becomes 250 times 8. Okay? So the function evaluated at 8 is just 250 times 8, which is 2,000. Okay, now, I've seen this a bunch of times. That is not correct. Okay, so once you get to this point, you're done. This is the input, that is the output. If you want to read this in terms of this problem, this means you can read 2,000 words in 8 minutes. If I want to write this as a pair, 8 would be my input, 2,000 would be my output. This is my x value, that is my output, my y value, in this case represented in function notation by w of x. Let's look at another one of those. Use the function in problem 3. So w of x is equal to 250x. How many words can you read in 6 minutes? So we now just place the 6 there, and we try to evaluate 250 times 6. So W of 6 is equal to 1,500, which means that in 6 minutes, you can read 1,500 words. Okay? So finding the range of a function. So the domain is, well, here's my function. The domain is 1, 2, 3, 4. What's the range? Well, my domain is all of my inputs. All I have to do now is calculate my outputs. So we're going to find f of 1, f of 2, f of 3, and f of 4. We're going to input all of these into my function and see what I get. So f of 1, that's negative 1.5 times 1 plus 4 gives me 2.5. Okay? Then negative 1.5 times 2, because now that's what I'm inputting into my function, plus 4 gives me 1. Negative 1.5 times 3, replace my x with my independent variable, gives me negative 0.5. And negative 1.5 times 4 plus 4 gives me negative 2. So now that I have my range, my output values for these input values, and it is a function because all of my inputs are different, okay? And my range would be 2.5, 1, negative 0.5, negative 2, written in order. That is option A. Okay? Our got it problem, my domain, the domain is 1, 3, 5, and 7. So to calculate this, we do the same thing. So g is the name of my function. I want to find g of 1. I want to find g of 3, g of 5, and g of 7. G of 1 would be 4 times 1 minus 12, which is going to be negative 8. G of 3 would be 4 times 3 minus 12, which is 0. G of 5 would be 4 times 5 minus 12, which is positive 8. And G of 7 is going to be 16. So my range is going to be, it's a set, okay, negative 8, comma 0, 8, and 16. The outputs from these 4 domain inputs. Okay, so you have 3 quarts of paint to paint the trim in your house. A quart of paint covers 100 square feet. The function A of Q equals 100Q represents the area, A of Q, in square feet that Q quarts of paint cover. What domain and range are reasonable for the function, and what is the graph of the function? Okay, so first of all, good names for my function here. Area dependent on how many quarts of paint that you buy. So let's think about this. What is the domain and range of reasonable? Well, you're going to the store, you're going to buy some quarts of paint, okay? So you don't go into Home Depot and say, can I get negative 2 quarts of paint? No, okay? So my domain has to be positive. You could go to the store and buy 0 quarts of paint. That would be weird. The guy would probably ask you why you were even in the store, but that is possible. Okay, so if I buy 0 quarts of paint, you cover 0 amount of area. Okay, so what happens if I buy 1 quart of paint? Now that would be 100. 2, plugging it right into my function, is 200 and 3, 300, and so on and so on. Okay, so there's my table. If I want to graph this function, table graph, let's make it a little straighter. Okay, so we got 1, 2, 3, 4. That is going to be paint, okay, in quarts. And let's just go 100, 200, 300, 400. And that is going to be area in feet squared. Okay. So pretty clear here. 0, 1, 2, 3, and then we can even extrapolate that 4 would give me 400. Now, the question is this continuous or discontinuous? So if we are going to draw this graph, is it possible to not use all the paint and paint a little bit less area? Sure it is. So this is going to be a continuous graph. All right. Let's look at our last got it problem here. If you have 7 quarts of paint, what domain and range are reasonable for problem 5? Well, the domain would be that your quarts of paint, if you have 7 and you can't get any more, right, the quarts of paint are going to be between 0 and 7. Okay, so the way we say that is less than or equal to Q, less than or equal to 7. Okay, because you could buy 0. You could buy, or you could use 0, you could use 7. Okay, so that's the domain. And my range becomes anything, right? The area of Q becomes anything from 0 to 700. Why does it not make sense to have domain values less than 0 or greater than 3 in problem 5, the one we just did? Because, or 7 in this case for this one, because you can't, like I said, you can't go buy negative paint. And did I make a mistake here? You have 3 quarts of paint. So this graph stops right there. Okay. So in this case, right, there was an upper limit. You cannot have any more than 3, like I put on the graph, but you can have 0, 1, 2, or 3. Or if you need more, then you go to the store and buy it. Anyway, Anyway, let's look at our last got it problem here. If you have 7 quarts of paint, what domain and range are reasonable for problem 5? Well, the domain would be that your quarts of paint, if you have 7 and you can't get any more, right, the quarts of paint are going to be between 0 and 7. Okay, so this graph stops right there. Our lesson check is identify the domain and the range of the relation. So we have my domain, -2, -1, 0, 1, and my range 3, 4, 5, 6. Represent the relation with the mapping diagram. And is this a function? Yes, this is a function. Is the relation in the graph shown at the right a function? Yes, it is, because it passes the vertical line test. And in fact, it is an absolute value function. What is f of 2 for the function f of x is equal to 4x plus 1? Well, let's do this. F of 2 is going to be equal to 4 times 2 plus 1, which is 9. So f of 2 is equal to 9. If I want to write this as a coordinate pair, I would have 2 comma 9. Domain is -4, 2. What is the range? So you just plug all these back into this function right here, and we get -2, -1, 0, 1, and 2. Write this using function notation. This is a good question here. So f of x would be equal to 2x plus 7. I chose x in there and not y because x is my independent variable. X is what is inside the function. Number 6, you can use a mapping diagram or the vertical line test to tell if a relation is a function. Which method do you prefer? A mapping well, it actually depends. A mapping diagram is better if you see if you just see the data, and the vertical line test is better if you see a picture. Student drew the dashed line on the graph to show and concluded that the graph represented a function. Well, it is true that that line does not touch the graph more than once. You have to look at the entire function. It's good over there. It's good over here. But right there in the middle, we're going to hit the function 3 times. Or we're going to hit the graph 3 times, which means it's not a function. It is a relation. Right? And that is 4-6, formalizing relations and functions.